Okay, everyone can see my screen? Okay, so again, apologize for the pure Zoom again today. I'm fairly confident that this won't happen again on Wednesday, but bureaucracy and stuff. Um, I think the baby is down for a nap right now, so you'll have fewer background interruptions and stuff. Whether that's a good or bad thing and makes the lecture more or less entertaining, that's up to you guys. Yeah, so any questions on where we are so far? Or just anything about how the classes run? Canvas, things have been going okay, right? You guys were able to upload homework 1, it seemed, right? You guys saw homework 2. Office hours were running smoothly. Did any of you guys get that document camera thing that I mentioned that hooks over your, yeah, okay, cool. I heard also that the GSF is going to give everyone whiteboards. Some fraction of those might be given out, or I guess if some of you show up on Wednesday, then I think the GFSF is planning on showing up that day to give everyone a whiteboard. So if you want to come to class that day. But yeah, where we were was we've been talking about conservation laws in our analysis here. If I can get this to scroll. Okay, there we go. So we started off talking about conservation of mass, and then we did a lot of things with the divergence theorem and stuff like that, and then eventually came to something called the continuity equation, right? And then we started thinking about conservation of momentum. And in order to do that, we had to think about what happens when the control volume is moving. It's not necessarily fixed, right? And if the control volume is moving, then what that means is that you have to worry about when you're taking this derivative right here of whatever quantity that you care about. You have to make sure that you account for the fact that it is moving. And so we derive something called the Reynolds transport theorem. Okay, there is a problem in the homework about that a little bit. And so, please pay attention to that and have fun with that problem. And it turns out that if you derive the Reynolds transport theorem and then apply it to the quantity called momentum, which is just rho v, it's a vector, right? Then you arrive at basically that the change of momentum inside this control volume looks something like this. Okay, and so in our conservation of momentum law, we know that basically the rate of momentum change is equal to the sum of the forces, and all of the efforts that we talked about in the previous lecture were basically trying to derive this left side of the equation. And we were successful in doing that. And now for the rest of this lecture, we're going to talk about this right-hand side of the equation, okay? We got somewhere into that a little bit when we started talking about body forces. And body forces are really easy. You just had to take a volume integral of those because basically every molecule inside our control volume feels the same body force, or it feels this body force basically, and so you can just take a volume integral of that, right? The thing that was a little more complicated that we just started getting into a little bit was this concept of surface forces. Okay, and the surface forces is basically, for instance, we can, we're just talking about definitions here, right? So we can define an S of n. This is S as a function of n, not S, times dot product or, dyadic product or cross product or whatever of n, but S is a function of n. That's just defined as like a force over area of the fluid that the n points into exerted on the fluid below here, like that, right? And the thing that we postulated was that this surface force depends on the position and the orientation of this surface. And that's where things start to get a little bit more complicated. For those of you that might not believe me, let me draw a few pictures. You guys have so several of you or most of you have taken a fluids class before. You guys have almost seen this sort of flow before, right? Now imagine if we had a surface in the middle of this flow that was pointing like this, okay? And we defined our n as in this direction, right? Then the stress vector at this location right here, can anyone guess what that stress vector would be, or just intuitively what it might be? Just unmute yourself and then just speculate. There's no reason why anyone should be able to know this or have it correct, but just what's your intuition on what do you think the stress vector might be at that location and this orientation?
It's not 0, is it?
Well, let's say which way is it pointing?
Is it to the right?
It would be that might be I mean, if I don't actually know the answer because I haven't done the calculation, but intuitively, that's what I would think, right? Because I have flow that's moving fast, or fluid that's moving faster up here than down here. And so you might expect then that the stress vector right here would be in this direction or something, right? Does that kind of make intuitive sense to some of you guys? You guys might imagine then that if I had a surface that we're now pointing in this direction. In other words, I was asking, if I were asking like, what is the force that this bottom part of the fluid exerts on the top part of the fluid? I might then expect that the stress vector here would point to the left, right? And actually by Newton's third law, these two stress vectors are going to be exactly opposite and equal to one another, right? Because, you know, if something exerts a force on something else, then it's the equal and opposite, you know. But, you know, you could think about other cases too, right? What if I have a surface that looks like this? Like that. In other words, what if I were asking, you know, in a fluid like this, how much force does this side of the fluid exert on this side of the fluid? And what direction? Obviously, it's a force, right? So it's a vector. Does anyone have any intuition on what that might be?
Also to the right, because like the fluid on the left is pushing the fluid on the right.
Maybe, yeah, perhaps. I actually don't know. If I had to guess off the top of my head, I might guess that it's 0, actually, because you know, if I were to like superimpose the fluid flow, like if I'm an object just sitting right here in the middle of the fluid flow, you know, fluid that's higher than me is going to be flowing in this direction relative to myself, and the fluid that's lower than me is going to be pointing in this direction or something, right? So there's going to be some sort of like, I'm going to want to rotate, but net like actual force that this side of the fluid is exerting on this side of the fluid, I might guess that it's 0, but I don't know. The point is that it's different, right? It's different depending on which way n is pointing. Does that kind of make sense? And so we know that, you know, this stress vector, the force that one fluid exerts on another, depends on which way you're actually oriented in the flow. Okay, so for complete, just because this gets confusing real quick, the way that I'm drawing it, I didn't actually write anything, I'm just gonna erase this. If you really wanna see this, you can see this in the recording and stuff, okay? But what we're gonna try and rigorously talk about today is basically what is S of n, right? Again, this is a vector, and what's the right way of, well, basically bookkeeping. What's the right way of determining what is S of n here, right? The way we're gonna do that is we're gonna use a pyramid, okay? That might be a surprise to you guys. You know, we haven't really thought about pyramids in a long time. But let's think about a pyramid here. So bear with me for just a second. I'm going to draw a pyramid that looks like this, or specifically a tetrahedron. Okay? There's 4 sides to this tetrahedron. There's the sides that's on the 1-3 plane. There's another side on the 2-3 plane, another side on the 1-2 plane, and then there's this face that's pointing diagonally. Okay? And then I'm going to call the unit vector that points out of this plane, call the unit vector that points out of this plane n. Okay? And what I'm going to try and do is calculate what my S of n is, or how much force, what my stress vector is at this plane right here. Okay, and so, you know, just arbitrarily, I'll just draw it in some random direction, S of n. Okay? And then because I'm going to calculate the force that the fluid out here exerts on the fluid inside this tetrahedron, then it needs to be an area. Then I need to multiply by an area, right? And so I'm going to call the area of this face, of this outer face right here, dA. Okay. Now, of course, there are 3 other faces too, and so let me, just for clarity's sake, let me draw the other 3 faces. There's one face that looks like this. Okay. There's another face that looks like this. And another one that looks like this. Okay, I'll call this face 1, face 2, and face 3. And then the reason is because each of these also have a normal vector, but the unit normal vector here this one, for instance, points backwards like that, right? Because the normal vectors always go out of a surface, right? Always go out of an enclosed surface. And this unit normal vector is just negative E1, right? Just staring at the axes here. Hopefully, if you can see the way I'm trying to draw this weird 3D pyramid thing, then you can agree with me that that normal is negative E1. So that's why I'll call this surface 1. Okay, and then of course this unit normal is minus E2, and this unit normal is minus E3. Okay, and then of course each of these surfaces also have a stress vector associated with those. Okay, but those, you know, obviously would not depend on my normal vector n here. They would depend on my normal vectors E1, E2, and E3. Okay. All right. So the game now that we're going to try and play now is we're going to try and express my S of n in terms of the stress vectors and in terms of E1, E2, and E3. Okay. And the way we're going to do that is what we'll notice is, so let's say that this tetrahedron is small. Okay. So as dV goes to 0, so as the volume of the tetrahedron goes down, then what that suggests is that all the forces on this tetrahedron must balance, right? That has to make sense, because if I have a smaller and smaller and smaller volume, I can't have a force on an infinitely small volume, because, you know, F equals ma, then A gets infinitely large, and that makes no sense, right, as m gets really small. Okay, so mathematically, what that means is if I do a surface integral over the entire enclosure, right, that has to equal 0, or the 0 vector. Okay, and now I've actually written out what each of those, what each of the different terms on the surface integral are, right? There's this face right here, right? The force on that face is this. Okay. And then there's the other three faces. Sorry. Okay. You guys with me so far? Does that all kind of make sense? This dA1, dA2, dA3 is basically just the area of this these different sides of the tetrahedron. Okay.
Professor, are we assuming that S is constant across the face of it then?
Yeah,
Across
we'll
the
just assume that the surfaces are kind of small, and so as they get smaller and smaller, then S is going to be constant across that, right? We kind of made that implicit assumption in most of the other derivations that we have with the conservation laws and stuff too, right? Yeah, but good question. Okay. So there are a few different simplifications that we can make. One of those simplifications actually we talked about in the example earlier with the plane, the flow between two plates example, and that's that this S of minus E1 can actually just be written negative. Wow, that's a terrible negative sign. I apologize. Negative S of E1, right? This is basically saying that, you know, if I have some sort of surface and some flow, and you know, I'm talking about the fluid on top, that is, there's the force on the bottom, then that's going to be exactly equal and opposite to the force on the bottom is going to be the force on top, right? That's Newton's third law, as we talked about, right? Okay. The other thing I'll mention is we can do just a little bit of math and actually figure out what this area is, dA1. I'm going to spare you guys the details of that, but maybe you can believe me that dA1 can be written in terms of dA times n dot E1. The way that maybe you guys can intuitively see this is that dA1 is just the projection of dA onto this plane here, onto this 2,3 plane right here. And the projection then of that is exactly equal to n dot E1, okay? Another way of thinking about this is if my n has a very small 1 component, right? If my n starts to become more and more perpendicular to the 1 axis, then this area should become smaller and smaller and smaller, right? You can imagine like if my 1 axis is pointing straight out at you guys, right? And my n starts to become perpendicular to that, then my plane is going to look more like this, and it's going to have a very small component. My plane is going to be more and more parallel to the 1 axis, and it's going to have a smaller and smaller component in the 2,3 plane. Okay, but play with this sort of geometry yourself if you don't believe me on this. Okay, so I'll just call this the projection of dA onto the planes. Okay. All right, so using those two simplifications, I can write a larger equation here, right? S of n, I can simplify this first term. I'm gonna divide out by dA. Everything is gonna have a dA in it, so I'm not even gonna write the dA at this point. Okay, this first term just becomes n dot E1 times S of E1, except a minus sign because of Newton's third law right here, right? So that minus sign comes over here. And by analogy, all the other terms are going to look pretty similar, except with E2 and E3. Okay. And pulling everything over to the same side of the equation, I get that S of n is equal to n dot, whoops, like that. Right? You guys see how I did that? I just basically distributed out or factored out a factor of n dot in front of everything here. And I get this. Okay? This quantity in this parentheses here, in this set of parentheses here, is this a vector, a scalar, or a tensor? Any ideas?
It's a vector.
It's a vector? What makes you say that?
Because the quantity, wait, did you say the quantity in the parentheses or the right side total?
This quantity in the parentheses, not
that's
the right side total.
Sorry.
Is this are we taking like the dyadic product of E1, SE1?
Exactly.
Okay, so that's a tensor then,
So that's a tensor, right? Another way of thinking about this is, as we mentioned, a tensor is a vector of vectors, right?
Mm-hmm.
This is a quantity where the E1 component of that quantity is the vector S of E1. The E2 component is the vector S of E2, and the E3 component is the vector S of E3, okay? Just to remind you guys again, S of E1 is a vector S, right? That is defined as the stress vector in the E1 direction. Or in other words, it's how much force the fluid at higher, let's say, X values exerts on the fluid at lower X values, right? If my 1 axis is pointing this way, then it's the amount of force that this top fluid exerts on this bottom fluid. That kind of makes sense? Okay, and likewise, S of E2 is a vector and S of E3 is a vector. They're completely independent of one another, right? Depending on whatever my flow happens to be, as we talked about in this sort of flow between two plates thing, they can all be completely different depending on which way I'm pointing in space, right? There's a priori, I know nothing about what those are. They're just completely independent factors in there, right? So we have 3 completely independent vectors, and we have a quantity who is a vector of those vectors, right? whose E1 component is one of those vectors, whose E2 component is another one of those vectors, and E3 component is another one of those vectors, right? And so that's why we call that the stress tensor. Okay, and the symbol that we use is a lowercase sigma like that. Okay, another way of writing this is that is S sub j of n is equal to ni times sigma nij, right? And this maybe hammers at home again, that S here is a vector, and the one component of that you can get by basically dotting n1 or dotting n with the first component of the stress vector or something like that, right? Let me write out what these things mean. We already talked a little bit about that earlier, but let me write out in words what the different components of the stress vector actually mean, okay? Sigma ij, okay, that is defined as the j component of the stress vector stress vector on a plane perpendicular to the I-axis exerted by the fluid at greater I. Okay. This is sort of what I meant earlier when I said, okay, in my stress vector here, or my stress tensor right here, right? The 1,1 component, for instance, is well, you can get that from, that's going to be the first component of S of E1, right? And so in that case, S11, I and j are both equal to 1, okay? And so it's the x component, if you will, the first component of this vector here, S of E1, right? Or in other words, to write it out, let me draw out something a little bit more pictorial also to maybe help you guys with that. If here are my three axes right here, 1, 2, and 3 again, okay? Let's say we care about the force that's exerted on a surface with a normal vector of E2. In other words, the force that this side of the fluid exerts on this side of the fluid, okay? That force can point in any arbitrary direction, right? Depending on what the flow profile actually looks like, depending on what the solution to all of our equations are, et cetera, right? And this is a vector, and that vector has three components, right? Those components are one in the 1 direction, another one in the 2 direction, and another one in the 3 direction. Let me draw that a little better so it's easier to see, and another one in the 3 direction, okay? And those components look like this. This component in the 1 direction is sigma 2,1. This one is sigma 2,2. And this one is sigma 2,3. Okay? Or to write it out mathematically, my S here of E2 is equal to sigma 2,1 times E1 plus sigma 2,2 times E2 plus sigma 2,3 times E3. I'm going to put a little star right here. I'll put a lot of stars right here and put a box around this. Because as we calculate forces and such in fluids profiles, you're going to need to remember this definition. Okay? Again, this is the j component stress vector on a plane perpendicular to the I-axis exerted by a fluid at greater I. Okay? So here's a plane. It's perpendicular to the 2-axis. Okay? And so sigma 2,1 is the first component of the stress vector. That's why it's this way, and that's why S of E2 here is written like this. Okay, Does that all kind of make sense? So just to remind you guys, if something isn't obvious, sigma is a tensor and it has 9 components, right? And part of the game that we're going to play then is how are we going to figure out what those 9 components actually are. I heard a question, sorry, I didn't mean to interrupt.
So is this the force exerted by the right side of the plane, so to speak, on the left side of the plane?
Exactly.
Okay, cool.
Yeah. And the stress vector the stress vector in general, as I mentioned over here, is exerted by the fluid into which n points. Okay, and so in this case,
N is E2.
in this case, it's E2, and because E2 always points in the direction of positive, of increasing 2, increasing y, I guess, if we're going to call it x, y, and z, right? Then it's the force exerted by this side of the fluid on this side of the fluid. Now, as we talked about with Newton's third law, if we happen to care about the force that this side of the fluid exerts on this side of the fluid, then it's just negative of that, right? So.
Is this related? Sorry, is this related to shear stress in any way?
Absolutely, yeah, we're going to get to that. Yeah, but just to give you a sneak preview, the shear stress, there are 2 components of the shear stress. Shear stress is determined by, is defined as, well, shear, I guess. So in this case, sigma 2(1) and sigma 2(3) will be considered the shear stress components. Okay. Okay, but this was a little bit of a tangent. Actually, it's a really important tangent. In fact, I even have a double-starred boxed equation here. It's a really important tangent. But it is a little bit of a tangent because remember, just to remind you guys, we started talking all about this because we care about the sum of the forces, right? And this is one of the, like the stress vector or stress tensor is a really neat way of tabulating all the different forces that happen, but only on the surface of a control volume, right? And remember, so this was the conservation momentum equation over any sort of arbitrary moving control volume, right? So let's go back to that momentum balance and let's now insert everything that we have learned so far. Okay, so let's go back to the momentum balance. Okay, left side of the equation is still the same. This is the change in the momentum inside our control volume. Okay, and the right side is just going to be the sum of the forces now. Okay, and remember we have body forces. Okay, these are body forces. And we also have surface forces. And now these surface forces is the stress vector. It's a surface integral of the stress vector on our control volume, right? Notice how I'm integrating of the surface that encloses our control volume. Okay. Can you guys guess what I'm going to do next to this term right here?
You're going to convert it to a volume integral? I'm
going to convert it to a volume integral using the divergence theorem, right? You guys have never done a divergence theorem so far on a tensor, but it works basically the same, works essentially the same way, right? Divergence theorem says that this surface integral right here is just equal to this volume integral. And because we spent all that time figuring out vector calculus and index notation and stuff, you guys now know what it means to take a divergence of a tensor. It's not that different from a divergence of a vector, right? And so this gives us this. Okay. And just like how we've done before.
Question really quickly.
Yeah, of course.
Is our control volume still, is it stationary or is it moving with time still?
No, it's potentially moving. It's a material volume, if you remember, right? It's this control volume that moves with the fluid and moves and deforms with the fluid. Okay.
Thank you.
Okay. And so we're going to do what we did, you know, with all the other conservation laws that we did. We're going to move everything over to one side of the equation. Okay, so if we do that, we get this. Like that is equal to 0. Okay, and then, you know, just like before, we noticed that our control volume or our material volume here is arbitrary, and the only way that if we integrate over a function that's defined in terms of position over any sort of arbitrary thing and always get 0 is if everything in the integral is always 0, right? So that means it's arbitrary, and so therefore the integrand has to be 0, and so therefore rho dv dt equals rho g plus divergence of sigma. Okay, and this is another equation that deserves a little box. It's an equation that even has a name. This is called Cauchy momentum equation. Okay, and if you didn't like my derivation, you can go into the book. You can find this as equation 6227. In index notation, this equation looks like this. Looks like this. Okay. Okay. So that's basically conservation laws. And the conservation laws that will basically get us through the rest of fluid mechanics is conservation of mass, which we found up here, just to remind you guys. That gives you an equation called the continuity equation, okay? And for most of what we're going to talk about in this class where the fluid is incompressible, it's just going to say that the divergence of the velocity field is equal to 0, okay? And today what we talked about is something like this. And it's another equation for the velocity, but it relates it in terms of the different forces that are in our fluids and the stress tensor. Okay? And so let's talk about a few different cases now of this. Whoops. Let's talk about a few different cases of this now. The first we're going to talk about, or the first case we're going to talk about is what's called a quiescent fluid. I hate that word. It sounds so much like we're in the ivory tower. All it means is that it's a fluid that isn't moving. Okay. And I'll show you guys that in this case of a fluid that isn't moving, this Cauchy momentum equation actually reduces down to something that you guys are already very, very, very familiar with. Okay. One of the things that we'll mention, or one of the sort of more obvious facts about a fluid is that a fluid cannot, fluids cannot support tangential stress, or as one of the questions that was asked earlier, was shear stress, basically, right? What this means is that only normal stress can be non-zero if the fluid is not moving. Okay. Just to remind you guys, from what we had earlier, I'll just reproduce that little diagram that we had earlier. Here's my axes 1, 2, and 3. You know, here's a plane in the E2 direction. The three components of my stress vector are going to look like this. This is going to be sigma 2, 1. This is going to be sigma 2, 2. And this is going to be sigma 2, 3. Okay. Now what I'm postulating here with fluids, and you know, should be pretty intuitive to our everyday experience, is that when fluid is not moving, sigma 2(1) and sigma 2(3) are both going to be equal to 0, right? Because if there were a force, if there were a force in either of those directions, then that would actually cause the fluid to start to move. Okay. What that means then is that my stress vector normally has 9 components, but if all of these components are going to be 0, if 2, 3, and 2, 1 are going to be 0, and by analogy 1, 2, and 1, 3, and 3, 1, and 3, 2 are going to be 0, that means that I can express my stress tensor like this. You guys remember what delta ij means, right? That's the Kronecker delta. Okay. And so what this is a lowercase p. I'm just writing a p like this so that you guys can see the difference between that and a rho. Okay. This just says that, if I wanted to write out my tensor as a matrix, this means that only the diagonal components of my tensor are non-zero. Okay. And the thing that I'm also assuming here is that all the elements of that diagonal tensor are going to be equal to one another. And one of the homework problems that you'll see, you'll show that that has to be true. Okay. Another way of writing this is my stress tensor can be written like this, or if you guys are more used to this as the identity tensor, then that's the identity tensor. Okay. Now, P here, you guys can probably guess what P stands for, right? That just stands for pressure. Okay. Now, when I write it like this, you guys could calculate what the stress vector would be, right? The stress vector inside the fluid in any direction is just S of n is equal to n dot sigma, right? But if I already defined what my sigma is, and it looks like this, then that's n dot minus p identity tensor. So I get minus pn. Okay. Does that kind of make physical, intuitive sense to you guys? The question is, if the question that I have is how much force is this side of the fluid exerting on this side of the fluid, or basically what is the, what direction, what is the force that this side of the fluid exerts on this side of the fluid? In this particular case, where n is E2, that's saying that my pressure is moving in this direction. My stress vector looks like this in this particular case, right? In other words, this side of the fluid is pushing on this side of the fluid with a magnitude equal to the pressure, right? Does that kind of make sense?
Is P a scalar?
P is a scalar, yes. I did not underline it. I did not double underline it or anything like that, right? And that's basically what pressure, what you guys might intuitively think about pressure, right? Pressure is, something is pushing against something else. In a fluid, it's basically every element is exerting a pressure on every other element, right? And that's basically what we're saying here. How much force is this side of the fluid exerting on this side of the fluid? Well, that's equal to P pushing in the minus E2 direction, as I've drawn right here, right? And of course, the force per unit area, right? That's sort of implicit here. And so if you want to know how much force, you multiply it by the area. Okay. As I mentioned, what you will show in your homework is that pressure is isotropic. So that pressure is isotropic. Okay. In other words, the diagonal elements are all equal. Okay. And so if we think about then what Cauchy's momentum equation looks like for quiescent fluids, for non-moving fluids, okay, just to remind you, or you can scroll up to your own notes. I can go back, but it's gonna take a couple clicks to get there. Okay, just to remind you what Cauchy's equation looks like. The left-hand side is dv dt, right? The material derivative of velocity with respect to time. In that case, I don't really have any velocity, right? And so the left-hand side of that equation gives me 0. The right-hand side of the equation gives me rho gi plus the divergence of the stress tensor. But the stress tensor in this case now looks like this. Okay. And so I get that. Oh, sorry, there's a typo here from when I copied down the Cauchy's momentum equation wrong. Okay. And the way I did this is because, as you guys know with Kronecker deltas, because I have a Kronecker delta ij here, I can replace the j with an I and I get this. Okay. In non-index notation, what this basically says is that the gradient of pressure is equal to rho g. Does that equation look familiar to any of you guys? It might look familiar to some of you guys. It might not for others. I'm going to go through an example and it'll show you exactly why that equation looks should look very familiar to you guys, okay? But this is called the hydrostatic equation. Okay, this is Dean 6311. Okay, in words, this basically says that the pressure gradient balances the weight of the fluid. Okay, because this side is a pressure gradient, obviously, and then this side is rho times g, g being the gravity force or something, and so that's the weight of the fluid. Okay. If perhaps this doesn't look that familiar to you guys, let's think about an actual situation where we have some amount of fluid inside, let's say, a beaker. I'll assign axes like these, okay? And I'll say that gravity goes in that direction. If gravity goes in that direction, then perhaps I can write gravity like this, where now this g is just a scalar that's equal to 9.8 meters per second squared. Okay. Then what that implies, using my hydrostatic equation up here, is that del P, the gradient of pressure written out, that looks like this. Okay, is equal to my G, or rho times G, right? And so rho G EZ. Okay, and so what that means then is that dP dx is equal to the x component on this side of the equation, which is a 0. So dP dx is equal to 0, dP dy is equal to 0, and dP dz is equal to minus rho G. And I can solve, that's just one of the simplest differential equations you'll ever find. I can solve the differential equation and get that pressure is equal to some integration constant. I'll call that P0 minus rho GZ. Or in other words, pressure is equal to rho GH. That equation all of you guys have seen before. Yes, nod your heads. Thank you. Okay. Does that kind of make sense to you guys? Now that was like the simplest case one could possibly think of in terms of the Cauchy momentum equation, right? Now, obviously, we're going to get into a little bit more complicated cases in this class. We're going to talk about fluids in motion. Okay. And what we will find when we talk about fluids in motion is that the stress tensor, it's actually convenient to break it up into two different contributions. Okay. And I'll say it has two contributions from both statics and dynamics. Okay. In other words, it's convenient for me to think about what the stress tensor would be if the fluid were not moving. And then I will think about the component that comes in, or the contribution that comes in when the fluid actually is moving. Okay. The way that I mathematically write that out is that my stress tensor right here is equal to minus P times this. That's the static component. We just talked about that up a little bit earlier, right? And then plus this guy right here. This piece comes about, as I said, this is the static component. This piece is called the viscous stress tensor. Okay. Some books, or some texts call this the deviatoric stress tensor. Okay. I'll just call it the viscous stress tensor. If I accidentally call it deviatoric, you'll know what I mean. Okay. Written out in the next notation, this says that sigma ij is equal to minus P delta ij plus tau ij. Okay. And the only reason we do this is because it just allows us to separate the stress tensor a little bit. And then it allows us to, this delta, or this tau ij will become really important later on when we talk about constitutive relations and stuff. And that's what we'll talk about in the next class probably. Okay. But I'll just mention that if we sort of take this on faith at this point, then the momentum equation becomes this. If I can write, becomes, okay, we started with a momentum equation that looks like this. Like that. Now our stress tensor is going to have two components, so I can actually write this derivative out, or in this case, the derivative is a divergence, as we know. It's equal to minus P times delta ij, and so I get minus sorry. Like that. Like that. Okay. This is just literally just me substituting this definition into here. Okay. And then this term I can simplify a little bit, right? Kronecker delta. And so I can replace the xj here with an xi. So I get that. Okay. And so my momentum equation looks like this. Or written out in terms of non-index notation to maybe be a little bit more familiar to everyone. This momentum equation now looks like this. Okay. I should mention there's something called a dynamic pressure also. It's kind of like how we separate the stress tensor into a component that comes about from both statics and dynamics. The dynamic pressure is defined as, or the Dean text likes to use this a lot. It's defined as a letter, as a curly P here, that's just written in terms of this. It's defined such that this equation is true, okay? It's basically the component of pressure or the contribution of pressure from fluid motion. Okay. The reason why we define it this way is so that we can basically just combine these two terms together and then we never worry about body forces. And so when we solve one fluid situation, it should be the same regardless of which way the body force is pointing and stuff. Okay. So the momentum equation then becomes this. Okay. And so we use this equation sometimes when we talk about basically the pressure that comes from the flow itself. We're not caring about the hydrostatic pressure, this pressure that we derived up here. This pressure equals P0 minus rho GZ or something like that, right? And so let me write that down. This is useful when we only care about the pressure from flow. Don't use this when we consider gravity. Okay, so if we're talking about like some sort of gravity-driven flow or something like that, then let's then stick with the original equation. Don't use this curly P here. Okay, but it'll become apparent which situations those are useful for and which ones are not. Okay, cool. So let me summarize real quick where we're at now that I have just basically a few more minutes left in the lecture. Okay, we have basically figured out most of the conservation laws at this point. What we have are basically 4 equations. Okay, those 4 equations look like this. Right? That's one equation. This is the continuity equation. Okay. We have another equation that looks like this. Okay. This is the momentum equation. I said I had 4 equations, right? I wrote down 4 equations here. If you guys don't believe me, this is actually one equation right here, because this is dv1 dx1 plus dv2 dx2 plus dv3 dx3 equals 0. Divergence of velocities equal to 0, right? This is actually 3 equations because it's a vector equation, right? This equation happens, this equation is true when I equals 1, this equation is 2 when I equals 2, and this equation is true when I equals 3, okay? And it turns out, so here are the 4 equations that we have, right? how many unknowns do we actually have in our system here? Here are the unknowns that we have. Okay. We have our velocities, right? VI. Okay. Let's say we're given what the body force is going to be, okay, or what the acceleration field is. Let's say it's 9.8 meters per second squared, and we know which direction it's pointing. Okay, that should be given in most problems. We don't know a priori what the pressure is going to be, so that's an unknown. That's a scalar, so that's 1. And then we have a stress tensor, tau ij. That's 9 unknowns, right? Because there's 9 possible components to that. So we have 13 unknowns, right? So we have 4 equations to solve to give us 13 unknowns, right? And so the conservation laws will only get us so far, right? We will be using conservation of mass, continuity, and conservation of momentum to get us these very fundamental equations, but that's not enough to be able to allow us to solve fluid problems, right? In other words, we need more equations. Okay, and we're not going to stop until we get them. We're going to stop today, but you know, let me get you guys somewhere at least a little bit closer along the way. There is an additional conservation law that I have not told you guys about. That conservation law is called conservation of angular momentum. Okay. That derivation is even more complicated than the momentum one. It gets really mathy. It's not actually all that important. I'll just tell you what the conclusion of that is. Okay. Conservation of momentum says that sigma and tau are symmetric. Okay. If you do care about that derivation, look in Dean. It's there. Okay, it's in the section on conservation laws and stuff. It is really interesting. I mean, look it over if you can understand it and figure out all the math and stuff. That's awesome. Go for it. But sigma and tau are symmetric. Okay, that hopefully makes some of our lives a little bit easier. We don't have to deal with all these like symmetric, antisymmetric things. There are cases plenty later on where we're going to be dealing with antisymmetric tensors and stuff, but we don't have to worry about like what is dotting with what, or we can, you know, remember how like if a vector and a tensor are dotted together, you have to make sure the tensor is symmetric before you can switch them, stuff like that. Does that sound familiar to you guys? Okay, anyway, if not, all right, great. Sigma and tau are symmetric, okay, and that allows us to eliminate 3 unknowns, and so now we have 10 unknowns. Okay, so we still have 4 equations for 10 unknowns. We have 10 unknowns here because, right, there are 9 components to a general tensor, but only 6 components to a symmetric tensor, right? We talked about that earlier when we talked about tensors initially. Okay, so we have 4 equations, 10 unknowns at this point. We still need more equations, all right? And so next lecture, we're going to start talking about where all those other equations are going to come from. All right, office hours tonight from Zhao, and then office hours again tomorrow, same time, for especially for homework 2 help. If you have any other questions, start a discussion or whatnot. Yeah, any questions overall in the class or anything going on?
For the office hours, last week I specifically emailed Zhao. I don't know if it's like something he can like always do, but can the office hours be recorded just because they're like 3 a.m. or 4 a.m. for me or something? But they'd still probably be helpful in terms of the discussion. At least last week they were.
Yeah, just remind Zhao basically. This is up to Zhao. Like it's sort of a question of like some of you guys might be more or less willing to answer or to ask questions and stuff. You know you're being recorded. I'll leave it up completely to the TAs on whether that's okay. Where are you such that office hours are 3 a.m.? Are you in like Germany or something?
Yeah, I'm still in Germany, but I'm coming back to campus in 2 weeks now.
Cool.
So until then, it's just nice to still. But yeah, I totally get if people don't want office hours recorded. That's obviously also fair.
Yeah, so I'll leave it up to the TAs who are going to be running the show during office hours. Okay.
Do you have time for a few questions about how to use the Kronecker delta?
Yeah, if any of you guys want to stay around for that, yeah, go ahead.
Great. Yeah, I was just wondering how
I'm
far.
gonna stop recording though,
Great.
unless you want me to keep recording. All right, I'll just keep it going. Go ahead.
So like the trick is you can switch the indices, one of the two indices to the other that's in the Kronecker delta to whatever other term you're applying it to.
Yeah, that's correct.
Does that also extend to the Levi-Civita symbol?
No, it does not. The Levi's, the permutation symbol is a lot more complicated than that. Yeah. I'll just say no,
Okay.
you can't.
Okay.
Yeah, you have to take it on like there's not like an analogous thing that you can do with a Levi-Civita symbol, basically. The reason that this comes about in the Kronecker delta is because, so for instance, if we were to stare at this term for a second, the reason is because we're summing over j here implicitly in this term, right? So if I can find a little bit of space here, this term implies a sum as j equals 1 to 3 of negative, crap, I can't write very well. Negative p delta ij dxj of this, right? And so I could write out what that sum would be. That sum is just going to be minus dp I1 dx1 plus, well, minus, I guess, minus dp delta I2 dx2 minus dp delta I3 dx3, like that, right? And only one of these terms is going to be non-zero, right? I can either be 1, 2, or 3. And so only one of these terms can be non-zero. The term where it's non-zero is the term where I is equal to that term, right? And so that's how this is just equal to minus dp dxi. Can you guys see how that works? Mm-hmm.
Okay.
Okay.
So for general like use, if there's a Kronecker delta in like multiplied by any other term, you can just switch one of the two, just whatever suits your interest more. Okay.
Exactly. Mm-hmm.
Thanks.
Okay. Any other questions? All right. If not, I'm going to sign off. Thank you guys. Hopefully,
Actually, just for the plotting, we're free to use something other than MATLAB. Is that basically?
yeah. Just give me a plot.
Okay. Are we going to be doing things with MATLAB in this class where it makes sense probably to do it in MATLAB just because then?
There's not that much MATLAB in terms of plotting and stuff like that. I might ask you guys to plot a few equations and stuff like that. If you already know MATLAB, then that's helpful. I'm almost certainly going to show some examples in MATLAB.
Okay.
There's going to be sums and stuff like that where it's just, and I know MATLAB, and so I like to do things like that. So.
Okay, perfect. Cool.
Okay.
Thank you.
All right, I'm going to sign off. I'll see you guys on Wednesday. Hopefully some of you guys in person.